Hey, you guys. We are back for the second installment of section 9.5 or 6 through the rest of chapter 9. And what we're going to be continuing to look at is chemical bonding and the basic concepts of that. Now, if you recall, this Lewis structures that we were thinking about, Lewis dot structures, created by Mr. Lewis over here, was a representation of the valence electrons. So for example, lithium has one valence electron, so the Lewis dot symbol for lithium would be Li with one dot on it. So that's for just the elements. Now we're going to get into drawing Lewis structures of compounds and molecules, which is something like water. And water has a Lewis dot structure that looks like this, and it is an indication of the number and arrangement of electrons in that molecule, or a molecule of water. And when we say electrons, we're talking about valence electrons. So let's get to it. Writing Lewis structures. So how do you write a Lewis structure? Well, the first thing you want to do is draw what's called the skeletal structure of the compound. Like I did for water, I just drew who it was made up of and who was in the middle, which element, showing what atoms are bonded to each other. Put the least electronegative element in the center. Now you might see a problem here since oxygen is not the least electronegative. So this applies to most things unless it's hydrogen, because hydrogen can never ever be in the middle. Hydrogen can only have, when I say the middle, I'm talking about the middle of two other things, like this, for example. This is a big no-no because hydrogen, remember its electron configuration, can only ever have two electrons. By doing this, you have given it four. So never ever do that. So most of the time, the least electronegative is in the center. Our next job is to count the total number of valence electrons, adding one electron for each negative and subtracting one for each positive. So for example, if you were writing the Lewis dot structure of ammonium, ammonium is NH4 plus, and that NH4 plus, nitrogen has 5 valence electrons. Hydrogen each has 1, and there are 4 of them. And then for that extra positive charge, you would subtract 1, which gives you a total of 8 electrons for the ammonium Lewis structure. Next is to complete an octet for all atoms except for hydrogen. Again, they only want 2. And if structure contains too many electrons, form a double and triple bonds on central atoms is needed. Now, when I say too many electrons, I don't really like that. I mean, it kind of means that you don't have enough electrons. So I think we need to come back to that, and we'll check on that when we start adding double and triple bonds. Usually double and triple bonds are added because you don't have enough electrons to give everybody an octet. But if you share, you will be able to. So let's do an example. The Lewis structure of nitrogen trifluoride, NF3, is given up here on the top of your screen. For the first step, since nitrogen is less electronegative than fluorine, put nitrogen in the center. You see it down here at the bottom of your screen. Nitrogen is now in the center. Step 2 is to count valence electrons. Remember, nitrogen has 5. See its electron configuration. Fluorine has 7. That would be a total of 26 for this structure or molecule. For step 3, draw single bonds in between those, and you see them, they just showed up down there on your structure. And now let's complete octets. So by completing octets, I can now check and see if I've gone over. So that's what the previous slide meant when it said if you have too many by completing octets, you must use double and triple bonds. So if you check it out here, nitrogen has 8, 2 as here is the lone pair, and then 4, 6, 8. These single bonds are 2 electrons each, and each fluorine thinks it has 8 also by sharing. So here's what the shape looks like of nitrogen trifluoride. The reason it's bent down this way is because there is a lone pair right here, and it's taking up space. So we'll talk about that more in chapter 10. So step 4, check that your number of electrons in your structure are equal. And sure enough, we went in with 26, and if you count your structure over here, you have 26. So there's an example of creating a Lewis dot structure for a molecule. Let's try another one for a carbonate anion. Remember, carbonate is CO3 2- up here at the top of your screen. And carbon is less electronegative than oxygen, so it's put in the center down at the bottom of your screen. Step 2 is to count valence electrons, and you see here, there's the valence electrons for each one. Total 24 for this structure. Draw single bonds in between like we did on the previous one. Give everybody an octet, which is what this textbook likes to teach of how to do it, and that's fine. So you give everybody an octet and then you count. And everybody has an octet, and that's what that's showing here by these red circles. But if you count the number of electrons that you've placed in this structure, I get 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. I get 26 electrons, and 26 is greater than 24. So we have put too many in there. So obviously there's not enough, so we need to share. So again, there's that 26, so it did not work. Too many, so we must form a double bond and recheck. So form a double bond. Now this is a little bit misleading, thinking that 4 electrons make a single bond, but it doesn't. It's just taking away 2 of the electrons, and then those 2 go down in between here. And there's your double bond. And that's what carbonate looks like. Carbonate structure is very flat, planar-like structure like this. It's called trigonal planar, actually. And that has a double bond. Now, I could have put the double bond in any place in this structure. It could have been here or here, but not in all places. Just one of those. So let's talk about fun sheet question number 6 and 7 for fun sheet number 9. Now, checking out as far as looking at Lewis structures, which is what you're learning about here. Lewis structures, like we've talked about before in this chapter, gives you an idea of how they're put together and in what order the elements in the compound. And in this example, or in this fun sheet question, the goal is to draw a Lewis structure for each of the compounds and then look at their electronegativities and draw a bond moment on each bond. Now, if it doesn't have a bond, now these bond moments are only on covalent bonds. So there is a compound in this list that is an ionic compound. So you would not have a bond moment on that. Now, if there's other covalent compounds, then you can draw a bond moment on each bond. Now, a bond moment is, let's do something like water. To review, water has a bond moment on each of the OH bonds because oxygen is more electronegative than hydrogen. So there is a bond moment pointing towards the oxygen, bond moment pointing towards the oxygen. So that makes the oxygen feel partial negative and the hydrogens feel partial positive. And then the overall bond moment, the overall molecular dipole moment is going to point upwards like that. So when you are doing this problem, keep in mind the size of your arrows for each bond moment, and remember that the bigger the difference in electronegativity between the elements, the larger the bond moment will be. And you're also to classify the substances as ionic, non-polar covalent, or polar covalent, and explain your answer, and then give their name too. And so we can you can practice naming. For fun sheet number 7, kind of the same thing. Write the Lewis dot structure. Indicate the total number of valence electrons per molecule, and then that's all. That's all there is for that one. So remember, if it's negatively charged, you would add an electron to your total. If it's positive, you would take away. The rest of these are neutral. And I give you a hint on your fun sheet about P4 and that each phosphorus is attached to 3 other phosphorus atoms. And that was a little bit challenging, but it's 3-dimensionally very interesting. So that's what you would want to do for fun sheet number 6 and number 7. Let's continue on with talking about Lewis structures, but now we're going to bring in what's called formal charge. Formal charge is a way to understand where the electrons are in a molecule, but also to help predict the most plausible Lewis structure. So let's look at formaldehyde for an example. Formaldehyde, we know, is CH2O. That's its empirical and molecular formula. But the question is, how is it arranged? Is it arranged like this or like this? Well, let's just play around with this Lewis structure idea in formal charge. Formal charge, by definition, is the electrical charge difference between the valence electrons in an isolated atom and the number of electrons assigned to that atom. So that sounds a little strange, but we'll do some examples. So, or you can use this little equation. This equation is to calculate formal charge again. The formal charge on any atom in a Lewis structure is equal to the valence electrons in the free atom they call it isolated up here, and you subtract the total number of non-bonding electrons, so those would be pairs, non-bonding electron pairs, and then you subtract out the half of the total number of bonding electrons. So that's like in a bond. So if you have a single bond between a carbon and an oxygen, this carbon is assigned one of those, and then the oxygen is assigned the other, and that's why there's a half involved here. So the sum of the formal charges of any of the atoms in a molecule or ion must equal the charge on the molecular ion. So if a molecule is neutral, if you add up formal charges, it must equal 0. If the ion is positively charged, then it must add up to give a positive charge. We'll see, we're going to play with formaldehyde to illustrate. So here's a possibility of a Lewis structure for formaldehyde. Formaldehyde, remember, was CH2O, and if you did your valence electrons, you had 4 plus 2, 1 each for hydrogen, plus 6 for oxygen. That's a total of 12 electrons for the formaldehyde structure. So here we have 2 for the bonds, the bond between hydrogen and carbon. So that's 2, 4, 6, 8, 10, 12, and that does fit. Okay, so let's look at, this is looking at formal charges. The formal charge on the carbon is equal to the number of valence electrons minus the non-bonding, you saw 2 up there, and then it's circled in red at this point, and then half of the bonding, those are circled in red, and you get a formal charge of -1. On that carbon, for oxygen, same procedure, valence electrons minus the lone pair, minus half of the bonding, and again, you get +1. So you have a +1 on the oxygen and a -1 on the carbon. So let's look at the other arrangement of formaldehyde. The other arrangement of a formaldehyde molecule would look like this. Again, your 12 electrons are accounted for. Let's look at the formal charges. The formal charges for carbon is 4 minus 0. Now that 4 is the valence electrons, the 0 is the non-bonding, and half the number of bonds is half of 2, 4, 6, 8 is 4. 4 minus 4 is 0. So we have 0 on the formal charge for carbon. For oxygen, again, same procedure, and we get 0. So the number of formal charges for oxygen in this arrangement of formaldehyde is 0. So the overall charge then is also 0. So this is the most stable arrangement of the formaldehyde molecule, and that is dictated by these formal charges. So what's the best case for these formal charges? For a neutral molecule, a Lewis structure in which there are 0 or no formal charges is preferable. Now you can say, how do you know that? We know it because it's been observed. We see molecules in certain ways, and when we apply the formal charge idea, the Lewis structures in which there are no formal charges are most prevalent. Lewis structures with large formal charges are less plausible than those with small. So you want very little formal charges, like a -2 formal charge is not as good as a -1, and so on. Among Lewis structures having similar distribution of formal charges, the most plausible is the one in which negative formal charges are placed on the more electronegative atom. So that means an oxygen would rather be negative than a nitrogen, or a fluorine would rather be negative than either nitrogen or oxygen. So let's look at an example. Here again is this formaldehyde. Is that a good one, or was it this one better? So looking at these two arrangements, this is going to be the better one because of the lower number of formal charges that was dictated by the arrangement of the atoms around the central carbon. So let's talk about your fun sheet question number 9 on this fun sheet number 9. The goal in this chapter was really to understand Lewis dot structures and to understand bonding. So in this one, there's different ways that things can bond or different ways that elements can come together to form a compound. And in this problem, your goal is to create Lewis dot structures for each one of these substances as they are put together and assign formal charges to each of the atoms in the compound. So let's look at one of these, and just as a real quick example, remember to do a Lewis dot structure. You first want to add up your number of valence electrons per molecule. So remember, hydrogen has 1 valence electrons, but there are 2 of them. And then carbon has 4, and nitrogen has 5, and there are 2 of them. So if you add that up, it gives you 10, 14, 15, 16. And so now the goal is to place those 16 electrons in such a way as to reflect how they're attached in this specific example. So the carbon is attached to 2 hydrogens, and then it's also attached to a nitrogen, which is attached to a nitrogen. So when I did that, I just used 2, 4, 6, 8, 8 electrons. So if I remember correctly, we had 16 electrons to use. 16 minus 8 is 8. So now somehow we have to fit in the rest of those electrons to make sure that everybody has 8 and follows the octet rule. So I'll let you guys work on that and do the same thing for the other ones. And then once you are finished with drawing the Lewis dot structure, determine the formal charge on each atom. And by doing that, the goal is to use formal charges as a guide to see which molecule is most stable. So now one of these is called cyanamide, and I gave you, this is a link to a Wikipedia site that talks about cyanamide. Another is called diazomethane. So go through the motions, though, of doing the Lewis dot structures, determining the formal charges, and seeing which one is more stable and which is which as far as cyanamide and diazomethane. So I'll let you guys work on that, and we can, and if you have any questions on that, of course, shoot me an email. So let's look at the concept of resonance. Resonance structures is one of 2 or more Lewis structures for a single molecule that cannot be represented accurately by only one Lewis structure. These types of things show up in, these resonance structures show up in compounds that have double or triple bonds. If a compound or molecule has only single bonds, you cannot have a resonance structure since there's no other way to orient those single bonds. But when you have a double bond, you can see that you could possibly put the double bond on this side or on this side. And we did see that on the previous carbonate structure we were talking about. This double-headed arrow is called a resonance structure arrow. So looking at the resonance structures for the carbonate, just like we were doing before, that double bond that we placed there could have been in between oxygen number 1, oxygen number 2, or oxygen number 3, and it wouldn't have made any difference. You would have gotten the same result. So that's what this is showing. These double-headed arrows are interconverting between the resonance structures of carbonate. So resonance structure number 1 down here, to get to resonance structure number 2, I could put this pair of electrons here, but then carbon cannot have more than 8, so that pair of electrons needs to be moved out. Then to go from resonance structure 2 to resonance structure 3, I could move a pair in here, but then this one is going to have to vacate since carbon cannot have more than 8 electrons. So for your fun sheet question number 8, just wanted to go over that with you really quick here. You're studying the cyanate anion, which is this OCN-. So the goal here is to draw 3 Lewis structures for cyanate that are using different arrangements of the available electrons. However, how is this going to be organized? And I found a Wikipedia site that was really great talking about the cyanate anion, but which one goes in the middle is going to be the least electronegative. And remember, carbon is the least electronegative. So leave it as OCN as far as instead of rearranging the atoms, leave it like that. And then draw 3 different Lewis structures that showed varying arrangements of the electrons. These are resonance structures, and resonance structures have those varying arrangement of electrons. After you draw them, reference table 9.2 in your book. Now, table 9.2 is bond length tables, and those bond lengths are indicative of the type of bond that's present between 2 atoms. So if you notice here, you have carbon single, carbon-carbon double, carbon-carbon triple. And as you go from single to double to triple, it gets shorter and shorter. That is because of the extra overlap that these electrons require. So these in this triple bond. So these atoms would have to be closer. So what I wanted you to do, and this is a little different from the fun sheet that was originally placed in your D2L shell, is I wanted you to compare the lengths of the single, double, and triple bonds of the CN and CO, because that's what we're studying in cyanate. And I gave you the triple bond carbon-oxygen bond length, and that was not included in this table. When I was doing some reading about it, carbon-oxygen bond length really only shows up in carbon monoxide. So you don't see it in anything else, and that's why it's not included in this table, because it's not as common. So if I told you that the bond length of the carbon-nitrogen bond in cyanate is 120.7 and the CO bond is 124.3, I was asking you to try to figure out then what do you think that the carbon-oxygen bond and the carbon-nitrogen bond in cyanate is? Is it a double, a single, or a triple, or is it somewhere in between? So take a peek at that, and then let's keep on going on resonance structures and Lewis structures and the exceptions to the octet rule. So some exceptions are, one of them is the incomplete octet, which means there's less than 8. So an example of that is beryllium hydride. If you count up the number of electrons in a beryllium hydride molecule, you find that it's 4. So really the only thing that you can do is this with beryllium, and there only is 4 electrons surrounding beryllium. Now beryllium is a metal, but he has a pretty, the difference in electronegativities between these two atoms is not that great to make it an ionic compound. So this is a covalent compound, but it's a compound with an incomplete octet. And then the shape that this guy turns out to be is linear with an angle of 100 approximately, depending on the compound, 180 degrees here. We'll learn more about that in chapter 10, just giving you some heads up. And there's a little picture of it. So for boron trifluoride, here's another one that can have an incomplete octet. If you count up the number of electrons for this Lewis structure, you find 24. The least electronegative is going to go in the middle. That is boron. So boron's least electronegative, he's in the middle, surrounded by 3 fluorines. Now this is drawn incorrectly as far as its shape, but it's not for its Lewis structure. There's all your total. Boron now has an incomplete octet. Boron's shape for this molecule is called a trigonal planar, and it would make sense that these guys, instead of being drawn like that picture, it's drawn like this, and that's trigonal planar with angles of 120 in between the atoms. And there's a picture of it. Again, exceptions are odd electron molecules. Something is an odd electron molecule, something with an odd number of valence electrons. So when you put them together, you get 11. This is really the only way to put this structure together, unless, of course, you have this single electron on the oxygen. I posted a video for you by the organic chemistry tutor who goes over this exact one and discusses why that the structure that you see here is more stable than this one. This one has the lone electron on the oxygen. Another exception to the octet rule is an expanded octet. Expanded is greater than 8. So it has to be with a central atom that has a principal quantum number greater than 2. So this means in row 3 or below in the periodic table. So I'm going to write row 3 here for you to remember that. So SF6, sulfur hexafluoride is your example here that we're going through. Sulfur has 6 electrons. Each fluorine has 7. 7 times 6 is 42 for a total of 48. And sulfur is the least electronegative. He goes in the middle, surrounded by the 6 fluorines. Again, another exception to the octet rule, and it's expanded. Drawing the Lewis structure, identifying the formal charge on each of the molecule, on each atom in the molecule, and labeling that charge, and then explain why it's stable. I'm thinking that has something to do with electron configuration, but I'll see what you guys think. Now let's change gears a little bit and go to bond enthalpy. It's not changing gears too much because we had to know how to draw Lewis structures and understand structures as far as more complex Lewis structures to understand how they were put together, so we could then understand that the number of bonds that were in a molecule. But bond enthalpy is the enthalpy change required to break a bond in 1 mole of gaseous molecules, and that's called the bond enthalpy. So when things happen, as far as the chemical reactions are concerned, bonds are broken. When bonds are broken, energy is required, and that's why you see this is positive. Here's another example. Energy is required, but it looks like the bond between 2 hydrogens is greater than the bond between 2 chlorines. That kind of makes sense because the chlorines are much larger, so they can't get close together. But then to make the hydrogen chloride bond, see now this is an HCl bond. These bond enthalpies as listed in your textbook are all positive. Now if I break a bond, it requires energy and that's positive. If I make a bond, the bond enthalpy becomes negative. Alternatively, when we look at a chemical reaction, such as, I want to go back a little bit and I want to say, let's say we take hydrogen and we react it with chlorine and we make hydrogen chloride, and that is a gas. Now, on this slide, you see that you have the bond enthalpy for the HH bond, the ClCl bond, and the HCl bond. Looking at these numbers, I would have to break the HH bond to the tune of 436.4 kilojoules. I'd have to break the ClCl bond to the tune of 242.7 kilojoules. But then I would have to make the HCl bond, and when I make that, 431 kilojoules is given off. So did I put in more than I got out, or did I get out more than I put in? That's how you can determine whether or not these reactions are endothermic or exothermic. Looking at the numbers, it looks like I put in more than I got out, and this would be an endothermic exchange. So as far as looking, these were all single bonds. When we were looking at these 3 enthalpies, here's a double bond. You notice the number is a little bit larger. And then here's a triple bond, and the number is even larger. So for bond enthalpies, the general trend is that the single bonds will have a lower bond enthalpy than the double, which will have a lower bond enthalpy than a triple. For average bond enthalpy, as far as looking at those bond lengths, the bond length table in your textbook is table 9.4, I believe. I'm checking just to make sure I'm right. I am. It's table 9.4. These bond enthalpies were discovered by looking at the enthalpy of a reaction and then backtracking to what the bond enthalpies had to be in a ton of different chemical reactions, just like the enthalpies of formation were discovered and defined in your textbook. So here's an example of how bond enthalpies are kind of determined. Here's H2O gas can be ripped apart into H and OH minus. There's an enthalpy for this reaction that can be measured. Now this OH gas, that can be ripped apart even further. So given that, the average bond enthalpies, because this was a bond in between an OH over here, and this is a bond in between the OH over here. So if this enthalpy of reaction is 427 and this one's 502, then since the process that was occurring was an OH bond breakage in both of these small reactions, the average bond enthalpy for an OH bond is 464 kilojoules. Your textbook, I'm looking in table 9.4, shows 460, and here it is, 460. So these are averages, so that's why some error can be introduced into using these numbers to figure out enthalpies of a reaction. Now I want you to notice in this table, there is for carbon dioxide, he has his very own carbon-oxygen double bond enthalpy. Compared to up here in the table, you'll find a carbon-oxygen double bond right here, and that one is slightly different, and that's because that's in carbon-oxygen double bonds in compounds. So for these enthalpy changes using bond enthalpies, if you break all the bonds in the reactants and to gaseous atoms to form bonds in the products, that's the enthalpy of reaction using bond enthalpies. So the enthalpy of that reaction is a function of the total energy input and the total energy released. Your book uses this kind of a little formula here, but I want to encourage you to just remember that the amount of energy that goes in to break bonds and the amount of energy that comes out when bonds are made, if you have one that's larger, you put in more than you get out, that would be an endothermic reaction. If you get out more than you put in, that would be exothermic. If you kind of got the same that you put in and you got out, your enthalpy of that reaction would be very small. And that's what this picture is showing you, just as my arrows were over here. This looks like you put in more than you got out, endothermic. You got out more than you put in, exothermic. So here's an example, just like that. Well, it looks like I was drawing that same reaction on the couple slides ago. This is showing that this hydrogen bond has to be broken, this chlorine bond has to be broken, and hydrogen chloride bonds, or HCl bonds, have to be made. Same thing with water. Hydrogen bonds have to be broken, oxygen bonds, but they're double at this point, have to be made, broken. And that's why you have to know what your Lewis structure is. We have to draw our Lewis structures in order to do these problems. And then OH bonds are made, and there's 4 of them. Over here, there were 2 HCl bonds made. So how do I use these? I just look at my Lewis structures, just like I was doing on the previous slide. So it looks like an HH bond is being broken, and that has a bond enthalpy of 436.4. An FF bond is broken. The bonds formed were 2 HF bonds. Here's your 2. And that for a total. So as far as this is what I put in, this is what I got out. It's like I got out more than I put in, and there's that negative sign, which means exothermic. So for fun sheet number 11, that's what we're looking at right here. Fun sheet number 11 is talking about bond making and bond breaking. So the goal for this question is to analyze the chemical reaction and to determine what is happening. Is there only bond breaking, or is there also some bond making on the product side? So I'll let you guys think about that, because it's kind of a short question, but it's still kind of a foundational question in the fact that analyzing a chemical reaction to see bond breaking and making can give you an idea of the thermochemical nature of that reaction. So in number 12, your goal is to calculate the enthalpy change from the bond energies. Now the bond energies on the previous slide, we did this HH bond. We saw that a hydrogen single bond, HH single bond, was broken, an FF single bond was broken, and then 2 HF bonds were created. Now you can go to your table in your textbook and find the bond energy values or bond enthalpy values for those individuals and add them up. So we have 2 of these, and then we have 1 of these, and 1 hydrogen, 1 fluorine, and you would add those up. And remember that when chemical reactions occur, bonds are broken on the reactant side. So we have broken over here on the reactant side, and then we have created on the product side. And to figure out the enthalpy of reaction by doing this type of analysis, you want to see the difference between the 2 sides. If more energy is put in to break the bonds than is given off when bonds are created, then that would be an endothermic process, and your value, your delta H, would be positive. If more energy is given off when bonds are created on the product side than is put in to break the bonds on the reactant side, then that's a negative value, and that is an exothermic chemical change. Now, when you figure out a value right here of whatever that value is, that's kilojoules per mole. So now the next goal was to look at how much energy specifically would be given off if I reacted 5 grams of whatever. Now I have this is 5 grams of the first reactant is reacted. So for this part number 1, you would want to do 5 grams of H2. So if I react 5 grams of H2, now remember, our enthalpy is in kilojoules per mole. So we need to take that to moles first. So grams to moles. And then we can use, just like in our thermochemistry, that's what this is. We can use for every 1 mole, we can use the number of kilojoules given off. 1 mole of H2. Now you notice over here on our balanced chemical reaction, that's 1 mole of H2, and the stoichiometric coefficient is also 1. But if you do have something like on number 4 that is 2, when you do this step that I'm talking about right here, you might need a 2 on the bottom of H2 for that kilojoules per mole. So again, these two problems are about analyzing thermochemically what happens during a chemical reaction as far as the bond breaking and making aspect. So try that, and then we will, if you have a question, go ahead and shoot me an email. Okay, let's go over Funchy question number 13. Funchy question number 13 is always a favorite of mine because I like to really look at structures like this and how what they mean. I mean, because this is how molecules are drawn and symbolically represented for chemists and pharmaceutical companies and drug molecules and you name it. These are organic molecules, so they have all of this information included. And what they have information included is the bonds. They have the number and type of atoms. Sometimes they don't have all the lone pairs. So for this one, I thought it was a fun example to say, I do love honey, and fructose is the main sugar in honey. So these molecules do become more complex, but we just have more bonds to keep track of. So for the reaction of fructose and oxygen, it creates carbon dioxide and water, other products, and that's either combustion or metabolism. So for this question, the goal is to really analyze the bonds of everything, to analyze the bonds of fructose and analyze the bonds of O2 and the bonds of CO2 and the bonds of H2O. And remember, in these bond enthalpy problems, the products on the reactant side, their bonds are broken apart. So the goal is to use bond analysis of bond breaking. So these are the reactants, and the reactants bonds are broken. And then in the products, as those bonds are broken, they had to have been broken and been rearranged somehow, the bonds are made. So they are created on the product side. So since they're created on the product side, remember those bond enthalpies, when bonds are created, energy is given off. When bonds are broken, energy is absorbed. And remember, if we can determine whether our chemical reaction is endothermic or exothermic. Remember, our goal for this one is to figure out the delta H of reaction for this using bond enthalpies. So if we have to somehow tabulate all of those bond enthalpies. So for this first part A, the goal is to first make sure the Lewis structures make sense to you and draw the Lewis structure for the individuals of carbon dioxide, diatomic oxygen, and water. Because in order to do a bond analysis, you have to have a Lewis structure that shows you all the bonds that are present. And this will help you find out the number and type of bonds that are broken or formed in that chemical reaction. And also on the structural formula of fructose, which is what's given up here, this is the structural formula, add in all the lone pairs on each oxygen atom. So that's that part of the question. Then next, count and list all types of bonds in the reactants and products and put them in this table down here. So for the first part, like for CH bonds, I would go ahead and look at fructose and I would start counting the number of CH bonds. Now you have to be careful because some of these right here are not expanded. But remember, carbon always likes to have 8 electrons around it and it has 4 things. So there are actually 2 CH bonds in this area here where I just pointed the arrow. So I can count 2 CH bonds here. Here is a CH bond. So that makes 3. This makes 4. This one makes 5. And this one makes 6. And this one makes 7. So there are 7 CH bonds in fructose and in all the reactants. So that's where we would put our 7. And then the bond enthalpy, we would go look that up from the table in your textbook for a CH single bond. And then the energy absorbed for the breaking of these bonds, you would multiply these two numbers to get this energy over here. So you would do that for all of the individuals. You find all these different types of bonds in fructose. And then you have the OO double bond in oxygen. And then as far as the products are concerned, so these on your table here, this is reactant. And then on your table, this is the product. So you do the same type of thing. And then the goal, you total up all the energy for the breaking, you total up all the energy for the creation of those bonds and see what the difference is. And if you get out more than you put in, it's exothermic. If you put in more than you get out, it would be endothermic. So that's what part B is for on this fun sheet question. And then part C is now using Appendix 2, just like we did in Chapter 6, to determine an energy of a reaction or an enthalpy of reaction by using the delta H of formation from Appendix 2. So if you remember, the direct method to get an enthalpy of a reaction using Appendix 2 is going and finding all those values, and then it's equal to the enthalpies of formation of the products minus the enthalpies of formation of the reactants. And remember, you have to make sure to multiply each one of those heats of formation by its stoichiometric coefficient. So if you forget how to do that, we go back to Chapter 6. Remember, there's some direct method, that's called the direct method, and there's some examples back there. And what I did give you in this fun sheet question is the enthalpy of formation for fructose, because that was not there in your Appendix 2, so that was included. So go ahead and give that a shot with counting bonds and looking at the energetics and comparing them to using Appendix 2, and see how close your answers are for Part B and Part C for those enthalpies of reaction.